So we're going to solve the problem, how many grams of aluminum oxide can be produced from 13.6 grams of aluminum? And then we have this chemical equation, this reaction to help us out. So this is a stoichiometry problem, and I know right away that it's a stoichiometry problem because it's asking me about the stoichiometric relationship, essentially the quantifiable relationship between different chemical species as they participate in a chemical reaction, or as I like to think of them, a Crepes egg or Crepes milk kind of problem. This is a lot like cooking. We're saying if I have this much of one thing, how much of this other thing do I need or can I make based on the provided recipe? And our chemical equation is really our provided recipe then. I know Miss Gross likes to think of these as the thing one, thing two. If I have this much of thing one, how much of thing two can I need, do I need or can I make? So whatever way helps you to identify that this is that kind of problem, go with that. So how many grams of aluminum oxide, so you want to make sure you can kind of find those, so aluminum oxide is right there, can be produced from, so that's saying I'm really starting with this. So this is my thing one, or I like to think of it as this is my crepes. Or no, this is like my eggs, sorry, this is my eggs. How many eggs, or thing one? So I'm gonna have 13.6 grams of aluminum is my starting material. And I'm trying to figure out, okay, produced, that says to make, which makes sense because this is reactant, product. So how much of this, how many grams of that, right here, can I make from that? So this is my crepes. This is just like a recipe kind of problem with just mathematically a few more steps. So I'm really converting in a way, which is why we do use stoichiometry is really just a fancy way of talking about dimensional analysis. If I have 13.6 grams, how many grams of this product of crepes am I going to be able to get out? So I need to take this grams and turn it into another kind of gram. A gram of a different substance. The problem with that is there is no one-step conversion between aluminum and aluminum oxide in terms of grams. I don't know how many grams of aluminum are in aluminum oxide. It doesn't really work that way. It's like saying how many eggs are in crepes. Well, I need my recipe to tell me how many of one thing I'm required to make of the other. So in stoichiometry, we're usually going to do that through moles because moles allow us to communicate between the macroscopic world where we can like weigh things and measure things and the microscopic world of like counting atoms. So most stoichiometry problems, and I can't say all, but most follow a general pattern of going of mass or some other measurable quantity of thing one to mole of thing one, because now we're counting. Well, if I have this many grams of aluminum, this is how many moles of it. To mole, but of a different substance, so to mole of thing two, and then back to a measurable quantity, because I don't have a molimeter in the lab, and so I need to get into a measurable quantity of mass. So mass to moles to moles to mass. Usually these two are about thing one, or your egg, your egg, and usually these two then are about thing two, or your crepe. So going from there, I'm going to start with the mass of thing one. What do I have or know to start? I have 13.6 grams of aluminum. Now I need to know how many moles of aluminum. Essentially, it's a way of going, I need to count these aluminum atoms. We're counting through weighing. So I need to be able to get to moles of aluminum next, because that's where I can convert between thing one and thing two. I don't know the mass relationship between aluminum and aluminum oxide, but I do know the molar relationship. We find that molar relationship in our stoichiometric coefficients, just the numbers in front of our balanced chemical equations. So in order to get to moles of aluminum, I'm going to need to cancel out grams of aluminum. And I can tell I'm setting it up properly because my grams will divide out. So I'm essentially going to be dividing the mass of aluminum by the molar mass of aluminum, which I get from the periodic table, and happens to be 26.98 grams for every 1 mole. And I usually say, you know, keep about 2 places past the decimal. If it has more than that, you can go ahead and round to 2 places, but don't limit your sig figs with your molar mass. So, of course, the question isn't at all how many moles of aluminum are in 13.6 grams of aluminum. This is about aluminum oxide. So my next step is so I'm here, I want to get to that other substance. So this is where I would use the molar ratio. I want to get into moles of aluminum oxide. But in order to do that, so that's my next step in my journey, in order to do that, I'll have to divide out by moles of aluminum. So what do I know? How many moles of aluminum will generate how many moles of aluminum oxide? I get that from the coefficients. So 4 moles of aluminum will produce 2 moles of aluminum oxide. So you can see divides out, divides out. Now if I stopped and did my math right now, I would have answered how many moles of aluminum oxide I could produce from this, but that's not valuable because that doesn't really mean anything in the lab. I don't have anything that measures directly in moles. So I need to convert that. I need to go, okay, well, this many moles would weigh this much. So I want to get back to grams. And in order to do that, you see that moles of aluminum oxide will need to be divided out. You know, these are the units of molar mass, right? Grams per mole, grams per mole. So we're really talking about the molar mass of aluminum oxide, which again, I have to go to the periodic table and then I have to do a little bit of calculating because aluminum oxide has it's a compound and it's more complex. So 2 aluminum, so I'm using that 2, not this 2, that 2 moles of aluminum. So there's the molar mass of 1 mole, so I need to multiply it by 2 to account for the fact that there's going to be 2 of them. And then I need to add to that 3 times the molar mass of oxygen. The 3 comes from here, and the 16 is coming from the periodic table. And when I do that, I'm going to find that the molar mass of aluminum oxide is 101.96 grams for every 1 mole. So if you had 101 grams of it, you have 1 mole of it. So now when you look at this is what I like about stoichiometry. If I have set my problem up properly, all of the units that I no longer am interested in, even the chemical that I'm no longer interested, which is my eggs, aluminum, should divide out of the problem. So grams of aluminum cancels out, moles of aluminum cancels out, moles of aluminum oxide divides out, and grams, this is of aluminum oxide, is left on the top, and that's what the equation is about, how many grams of aluminum oxide can be produced. So then the next step then is to do the math, put it into your calculator, and you can do that in various ways. You can do 13.6 times 2 times 101.96 and then hit equals, and then go divide by this and hit equals, and divide by 4 and hit equals. You can put it in all at once, but you usually have to make sure you put in parentheses. So 13.6 times, well, I usually skip times 1s. 13.6 times 2 times 101.96, parentheses, divided by, and then you put these in, by multiplied by each other. So you're dividing by, but these are multiplied, going this way. Put that in, or you can multiply all the numerators together and write that number down. So you get like number x, and then you multiply all the denominators together and you get y, and then you do that. Either way, you should always come up with the same answer, which would be 25.6978, etc., moving on, grams of aluminum oxide. Now, the final step that we should always do, though, is to consider sig figs. So looking back through my problem, I have 4 sig figs. These are considered exact numbers. I have 5 sig figs here. This is only 3, so this is my weakest link. So 3 sig figs right there. So I'm going to round to 3 sig figs. So my final answer is going to be 25.7 grams can be produced of this aluminum oxide if I started with this. Now that's a theoretical number. That's like the absolute max that can be produced. I might not really get that because some might, some aluminum might not cooperate. I might have a spill, but this is the absolute most that could be produced if every single atom cooperated and was collected. And that is stoichiometry.